All right, now it's time to talk about titration curves. So over the course of a titration, the pH will change. Oops. And as you add the titrant, the pH will either increase or decrease. If you are adding a base, then the pH will get bigger over the course of the titration. If you are adding an acid, hey, could you go do that over there? Because I see Leonardo, but you're being loud and I can't concentrate on what I'm doing. If you're adding an acid, then the pH will decrease. And so that's just a feature of the plot that you can look at and just sort of understand which one is in the burette versus in the flask, right? So the analyte is down here and the titrant is up there. So the way that most titration curves are created, Michael, baby, clear up. Thank you. The way that most of these titration curves are generated is you have some sort of a pH probe. A probe is a type of an instrument that will measure the pH, and you put that down in the analyte. And so here in the flask you have the analyte, and you also have the pH indicator. All right, we've already talked about that. So the probe and the analyte and the indicator all go in the flask, and the only thing in the burette is the titrant. On the graph here, the x-axis at the bottom is the volume of the titrant that's added. All right, so it's always in volume. And notice that at the beginning of the titration, when there was 0 titrant added, the pH was low. That means that you have an acid in the solution to begin with, and the titrant must be a base, because notice as you add volume, the plot increases. And this here on the y-axis is just the pH that's being measured by the probe. So at the equivalence point, that's where the moles of the analyte and the moles of the titrant are equal, and you can spot the equivalence point because it is halfway up the vertical portion of the plot. Hang on, buddy. So there's a couple other features here that you can find. So here's the titration of a strong base into a strong acid. So we say it's the titration of a strong acid because that is what is in the analyte. So it's a titration of the analyte is the wording there. And notice that the strong acid starts with a very low pH, but on this one over here to the right, it's a weak acid, and I can tell that for 2 reasons. The first one is that it's got a higher starting pH, right? So before you add any of the base, the pH is a little bit higher. So that could not necessarily mean that it's a weak acid. It could just mean that it's a very dilute strong acid, a very, very dilute strong acid. And so the second hallmark is the location of the equivalence point. So we've already defined that the equivalence point is halfway up the vertical portion of the plot. So if you look where it kind of levels off here and here, halfway between those 2 lines, that's the equivalence point, and notice that it's at a pH of 7. For the titration of a weak acid with a strong base, notice the equivalence point, if we try to mark where the plot goes flat, the equivalence point is here. Notice it's a little bit higher, and it's close to it's close to 9, right? A little bit under 9. So for the titration of a strong acid and a strong base, the pH at the equivalence point is 7, right? That's true. Okay, this will always be true. You should just memorize that because that is one indicator that you're dealing with a strong acid and a strong base when you have a pH of 7 at the equivalence point. Now, we're going to talk a lot more when we get down into the weak acids and bases about why the pH is not 7 when you're dealing with a weak acid or with a weak base. But I'm not going to worry about that right now. We'll just kind of, I'll just tell you, we're going to talk about this later. But that is one thing that you can find. And so what this would be important for, why do we care? Like, so, oh, let's do that. Let's say, so what? So what? Why do I care what the pH at the equivalence point is? The pH at the equivalence point will determine which indicator you can use for your titration. So when we were looking at that in the last notes, and we said that, oh, there's a bunch of different, this slide right here, oh, there's a whole bunch of different ones. Knowing what the pH at the equivalence point is would determine whether you want to use something over here or something over here. And so that's one reason that we even care about that. So there's one new thing as far as math goes that we'll talk about. Good grief. Okay, sorry about that. We just struggle to share toys is the problem. Go away. All right, so this slide is just to show you what it would look like. In here, we are starting with an acid and we are titrating a base because the pH increases over the course of the titration. Whereas in this one, we're starting with a base as the analyte and we are titrating the acid into it because the pH decreases as you add the titrant. So that's the purpose of this. Let's look real quickly at this last slide because this is a new type of calculation that I want to show you guys. Sorry, I just noticed something strange. I hope this is recording. Oh, brother. There's some numbers down here I don't recognize. Okay, so the new thing that we're going to add to this, so it's a normal titration problem, gives you the volume, how can we say this? So a normal titration, you have the volume at the equivalence point and of the titrant and its concentration and the volume of the analyte, right, that you started with. So those are the three things that you typically have in a normal titration calculation. So what we're going to do now is we're going to change the question a little bit, and we're going to say over the course of a titration. Ooh, by the way, let me scroll back and say one thing. So the way that the equivalence point works here. So if we were doing, say we were doing this titration right here, and we had some HCl, and we were titrating it by adding a little bit of NaOH to it. When you get to this point right here, the equivalence point would still be colorless. But notice how vertical this line is right here. If you add just a tiny, tiny little drop, right? So if we were to add just a little bit of the base, right? I can't draw the lines very straight, but see how high the pH would jump. So it's colorless at the equivalence point, but at the end point, a very small drop of the titrant changes the pH drastically, which is why if we're using, say, phenolphthalein that we talked about earlier, the phenolphthalein would turn pink after just one more little drop of the base, because the equivalence point is the last moment that it can stay colorless. At that point, after you're adding even just a little bit more, the pH jumps so quickly that it quickly gets into the basic territory. That's why you want the color at the end point to be a very, very pale color, because otherwise it would show that you've gone too far and you would think you needed to add more volume than you actually needed to get to that point. Okay, so moving back down to here, we can calculate the pH of the solution anywhere during the course of the titration. So if you had a probe in the analyte, you would see the number, whatever the pH is. But if we just wanted to stop and say, what is the pH right here after I've added 10 milliliters or 20 or 30 or 40, right? We could calculate that using stoichiometry. And so this is not going to be a new type of a calculation, really. Essentially, what you're going to need to do is you're going to want to find out how much H plus or OH minus is left in solution. And this is why I say, and then of course you would use this information to find the pH using the concentration, right? So you would find concentrations of these guys. This relates back to when we found the concentration of ions in solution after a reaction. That was something that we did in the solutions unit. So everything's sort of coming back together. So first of all, let's fill in, we're totally balanced here, MV moles. So let's see how much we have used up of these two guys. One of the reactants will be limiting, right? It will be used up. And so we're looking for essentially the excess reactant, right? The excess reactant, if it's the acid, will have more H plus, or if it's the base, will have more OH minus. And so we can calculate pH from that. Let's just on with it. So the concentration of the NaOH is 0.12. The volume that we've added is in liters, 0.0253. And we've got 20 mils, so 0.02, and 0.25 molar there. So we need to multiply both of those together. 0.12 times 0.0253 gives us 0.003036 moles of NaOH, and we'll do the same calculation for HCl. 0.25 times 0.02 gives us 0.005. All right, it's a 1-to-1 ratio, so we can just automatically assign this guy as the limiting reactant, and this one is in excess because I will run out of 0.003 before I run out of 0.005 when they're used as a 1-to-1. Okay, so what we need to do now to find out how much is left over, well, now I can tell you that because the HCl is in excess, we will have an acidic solution. All right, so we would be toward the bottom of a pH of the titration curve, right? We'd be in the low pHs. And to find out exactly how acidic, we need to know what is the concentration of the H plus at this point. So kind of like what we've done before, step number 1 will be to use the limiting reactant to find out how much of the excess was used up, and then we will subtract subtract the excess starting minus excess used up. This will tell us the number of moles in the solution. And now we have to be thoughtful here. When we find the concentration of the H plus, we need to do moles over total volume. Remember, total volume is now going to include everything that we mix together, because in a normal titration, when you're finding the concentration, you want to know of the analyte, you want to know what is the concentration at the beginning before you added any titrant. But now we want to know what is the pH of the solution as it is right now, which means we need to combine the volume. So the total volume here will be the combined. And then the last step will be to calculate negative log of that H plus that we find. So let's just jump on in. The limiting reactant was 0.00306 moles of NaOH. I hope you see this before I have to write it all out. It's a 1-to-1 ratio. So really you don't even need to write it out. So that means we have 0.003036 moles of HCl that is used. Okay, so that was step number 1. Step number 2, we're going to subtract. We'll say 0.005 starting moles minus 0.003036 used up moles. 0.005 minus 0.003036. I got 0.001964. This is the moles of HCl left, right? So check here, we subtracted. This is how much is in solution still. Next we need to find the concentration of H+. So concentration of H+ is going to be this number of moles, right? Because it's a strong acid, so it will have dissociated. So we have that many moles of H+. And then we're going to divide it by the total volume, which is basically 20 mils plus 25.3, so that should be 45.3. So 0.0453 liters, and we divide 0.0453, and I got 0.04. 3355 molar H+. And then finally, step number 4, we take this number and we plug it into the pH calculation. Negative log of H+, negative log of 0.043355. And my little piddly calculator is not going to tell me that. So let me get my good one. Hang on. Okay, I got a pH of 1.36. This is an acidic pH, so it does make sense for the pH to be that low. If we have notice that the volumes aren't all that different from each other, but the acid is more concentrated, so there should be a higher concentration of H+ than OH-, and this pH down here makes pretty good sense.